for the test on Friday. Can talk a little bit about some of these. The test on Friday will cover binary inputs. Again, that's comparators, Schmidt triggers. Comparator is when the voltage I set is the same voltage that I clear. Schmidt trigger is I turn on at 1 voltage, say turn on at 2.5 volts, turn off at 2 volts. If there's a dead zone in the middle, that's a Schmidt trigger. That's for binary inputs. Binary outputs is either a resistor or a transistor used as a switch. A resistor is used, we can get away with a resistor if the load is less than 5 volts and the load needs less than 25 milliamps. That's just like an LED. Pick the LED or pick a resistor to set the current to the LED. If I need more than 5 volts or more than 25 milliamps, like if I want to drive a 5-watt LED or a DC motor, 8-ohm speaker, any of those, I'll need a transistor. So there you use a transistor as a switch. The collector sets the current and the base resistor saturates the transistor, so the beta IB is more than IC. In terms of assembler programming, see, fourth one. Go through a couple examples in just a sec. Got assembler programming. If I have a bunch of assembler commands, what do they do? What's the contents of the W register and other registers after each line of assembler? We'll talk about that in a sec. There's timing in assembler. If I have a routine, how long does it take to execute? Or how do you modify that routine so that it plays the note, say C3, 220 Hertz? Converting C to assembler. If I give you some C code, what's the corresponding assembler? We did that on the second homework set, such as if then else statements, converting that to assembler, do while loops, just short little snippets of C code, converting that to assembler, and flowcharts to assembler. And let's kind of go through an example of that. We go under homeworks and solutions. Let's take the first test from last semester. So for this one, again, this is first problem was digital inputs. Come up with a circuit that outputs 5 volts when the temperature is greater than 65 C, 0 volts when less than 65 C. That's a Schmidt trigger. There, the trick is pick a resistor. Actually, first calculate the resistance at your two temperatures. At 65 C, it's 212 ohms. 55 C, it's 301 ohm. Pick a resistor to convert that to a voltage, and something in that range of 200 to 300 ohms tends to work well. So this is on at 2.57 volts, off at 3 volts. The voltage where it turns on is the offset. For the plus minus, as the voltage goes down, the output goes up, so connect the minus input. And the gain, the output changes by 5 volts as the input changes by 0.5 volts, gives a gain of 11. Pick that to be 11 to 1. And that gives you a Schmidt trigger. This would go to a binary input on the pick, say port C pin 0, port B pin 0. That's one type of problem you can expect. On binary outputs, if I want to drive something at less than 5 volts, less than 25 milliamps, just use a resistor. For example, to drive an LED at 25 milliamps, see what I want to do. I want to drive it at 20 milliamps. Being an LED, this has a 3.3 volt drop at 100 milliamps. Being a diode, it's the same for all current, roughly the same. So this will also be about 3.3 volts at 20 milliamps. If the diode drops 3.3 volts, the remainder goes across the resistor. 1.7 volts at 20 milliamps is 85 ohms. If I want to drive something at more than 5 volts, more than 25 milliamps, I need a transistor. And in this case, if I want to drive a 500 milliwatt LED at 150 milliamps, that right there tells me I've got to use the transistor. The PIC can't drive 150 milliamps. So set this up to drive 150 milliamps. In this case, the transistor has a 0.2 volt drop when it turns on. The LED has a 3.3 volt drop, leaving 1.5 volts across the resistor. 1.5 volts at 150 milliamps is 310 ohms. If this is 150 milliamps, beta is 100. This has to be at least 1.5 milliamps. So pick a current bigger than 1.5 milliamps, less than 25 milliamps. I chose 5 milliamps. 5 minus 0.7 over 5 milliamps is 860 ohms. That's RB. And there's lots of right answers for RB. Anything between 1.5 and 25 works. Third problem is given W, port B, and port C have some initial values. What happens after each line of code? So the first instruction is move port B to W. That's the read command. So I take the contents of port B, move it to W. So that number changed. I'm now going to add port C to W, put the result in port C. So 9 plus 4 is 13. Put the result in port C. Port C becomes 13. I'm now going to AND W with 3. 3 is 0, 0, 1, 1. W and 3, 9 and 3 is 1. Again, this clears out all bits except the last two. 9 is 1, 0, 0, 1. I cleared everything except the last two bits. That's 0, 1. 0, 1 is binary 1. Let's see, right here. I decrement port B, put the result in port B, so 9 goes to 8. Increment port C, put the result in W, so 13 goes to 14. Port C stays the same. The 14 is stored in W. I bit toggle port B pin 0. So whatever bit 0 was, 0, 8 is 1, 0, 0, 0. Toggle the first bit, I get 1, 0, 0, 1, or 9. And then clear port C becomes 0. That's kind of something you expect on the test as well. Just a list of assembler commands and go through it line by line. What happens to W and the different ports? Another type of assembler, kind of mentioned about timing. Given this code, calculate how many clocks it takes to execute it. And in that case, it's just counting. In this inner loop, I've got 1, 2, 3, 4, 5 instructions, plus 1 for goto. Those are executed 127 times 4 times 247 times. The red section of code has 1, 2, 3, 4, 5, 6, 7, 8 instructions, plus 1 for goto. That's 9 clocks times 4 times 247. The blue section has 4 instructions plus 1, takes 5 clocks times 247, executed 247 times, and the black part is executed once. So the total number of clocks is 762,989. The second part is modify the code so it takes a certain number of clocks. In this case it was 1, 2, 3, 4, 5, 6, 7 clocks, plus or minus 1,000. Kind of one way to do that is pick something like this 127. The current code is 762,000 clocks. I want it to be longer, so that number 127 should be bigger. Scale it, and I get 205.49. Now go back and try. The A times B times C, I'm close. I'm 9,000 clocks low. I can get more accurate. Each count, or each instruction over here, each no-op, is called 247 times 4 times. So if I add a couple no-ops in there, I can trim the code and get within 300 clocks. And here's basically the easiest way to do that is take these existing numbers and just modify them. Come up with something that gives you something close to 1, 2, 3, 4, 5, 6, 7. If you need to trim it, I can add no ops to change the length of the code slightly. So I'll have one question on timing. The last one will be a flowchart. For example, what this one does is when I hit RB0, I want to have RC0 turn on for 0.123 seconds. The reason for the 0.123, that was homework problem number 4. This wait loop becomes 0.123 seconds, 1.23 million clocks. When I hit RB0, RC0 turns on for 0.123 seconds, then RC1 turns on, then RC2 turns on. The flowchart to do that is as follows. On the last problem, if you get stuck and you don't know how to do some parts of the code, just do what you can do. The way I grade it is each block was worth the same number of points. I think it was like 3 points per block. If I skip the first one, skip the second one, and do this one, at least I get partial credit. Each block should have a section of code. For example, on this one, port B is input, port C is output. That's the tris command. If I write 1 to a pin, that makes the pin output, 0 makes it input. So to make all pins on port B input, I write FF to tris B, which is move FF to W, move W to tris B, and everything goes through W. To make port C output, I clear tris C. That's the first block. That's 3 points. This arrow, that arrow indicates a label. I've got to have some place to jump to, so there's my label to come back to. RB0 equals, pressed is a 1. If it's a 1, I skip out. 0, keep checking. That's this guy. And I kind of like just guessing. Let's do a bit test skip if clear, or bit test skip if set. Guess 1 and see if it works. If it's a 1, I skip out. 0, keep testing. So if it's a 0, it's not set, I don't skip. Go back to loop. On 0, I keep looping. On 1, I skip out. So this implements that second loop, second block. I want to turn on RC0. One way to do that is just say, that's not assembler. Move 1 to W, move W to port C. And then to wait, that's just the subroutine from problem 4, call wait. To turn on port C pin 1, that's move 1 to W, move W to port C, call wait. Turn on RC2, move 2 to W, move W to port C, call wait. Or another way to do that, another perfectly valid solution, is I will set bit 0, call wait, clear bit 0, set bit 1, call wait, clear bit 1, set bit 2, call wait, clear bit 2, repeat. Another way to do it. There's always multiple ways to do it in assembler. And that's kind of what you can expect for the test on Friday. Again, some binary inputs, binary outputs, assembler programming, like the first one, given the assembler code, what happens at each register, some timing, converting a flowchart to assembler, and maybe some C to assembler, like the second homework set. Again, for the test, you'll have 1 hour in class if you take it in class. At home, you've got 2 hours, so you have time to download the code, upload the code. It takes a little bit of time. You also have the assembler command list, so you don't have to memorize it. This will be on the test as well. So you don't have to memorize the assembler commands, but you do have to figure out how they work and how you piece them together to do what you want. So that'll be the test for Friday. Again, this guy's available on the test on Friday.